Well, skewness is a nice statistic. It tells you how symmetric your values are. But in order to assess normality, we need a little bit more advanced tools. One of the tools is graphical tool. It's called quantile normal probability plot, or for short, we will call it quantile plot or even QQ plot. The idea is following. So you remember that if X is normally distributed values, then we can write an expression that describes this normality here, right? So we know that X is a combination of random values taken from normal distribution, Z, and then two parameters, mu and sigma, which are parameters of your population the values come from, right? But if you look at this expression, and then you recall how line looks like, so this is an equation of line, you can see a lot of similarities, right? So you can see that, for example, X is the same as Y here, Z plays the same role as X here, and then the parameters A and mu and sigma plays the same role as the intercept and the slope, right? So in this case, mu is intercept and sigma is a slope. However, in this case, we need to learn how to actually to estimate X and Z, because if you want to make a line and if it's experimentally based values, they should not be derived one from the other like we used to do this for Z-scores, right? So we need to find out how to estimate Z-scores kind of independently of X. So let me explain this. The intuition is following. If you indeed have normal distribution, standardized normal distribution, then every Z-score, it has a probability to find Z-score smaller than given. That's what we call sample quantiles. For example, if you think about, like this is normal distribution, if Z-score is equal to 0, then this area will be equal to 0.5, right? So it means that for Z-score 0, this probability is 0.5. So we can say that sample quantile is 0.5, right? If Z-score, for example, is -1, we know that for plus -1, we have approximately 68% here, a little bit more than 68% here. So it means that we have a half of 1 minus 0.68 on both tails. So this is approximately 0.16, right? So this is the precise percentile and so on and so forth. So we can find this simple quantiles for any Z-score. We can also do it other way around. If you know a quantile of a value, we can compute Z-score based on this knowledge about theoretical distribution. That's exactly what we are going to do. So the procedure is following. First, we compute sample quantiles based on ranks. So we use ranks, we use non-parametric approach to compute sample quantiles. So that's the first quantile in this name. Then we compute theoretical Z-scores based on this empirically computed sample quantiles and ICDF function for normal distribution. So that's the second quantile, because we are using quantile function here, right? And then finally, we make a plot X versus Z, which is computed based on these two steps, first empirical quantiles and then theoretical quantiles. And then if this plot shows the linear trend, then we kind of can assume that indeed our sample, our values came from normally distributed population. If not, then they can be different interpretations, which I'm going to discuss in this little video here. Okay. So let me show you this on a real example. I use the same values, concentration of chloride in milligrams per liter in 10 glasses of water. This is my sample size is n. And first of all, I need to compute these empirical quantiles based on ranks, right? So I compute ranks. For example, you can see this is the smallest value, so it has rank 1. This is the largest value, so it has rank 10. So I have a rank for every value. And I compute quantiles based on these ranks. You remember how we compute quantiles? The sample quantiles, right? So sample quantile, it's the rank of this sample minus 0.5 divided to the sample size, right? So for example, this rank is 1 minus 0.5, it will be 0.5. And then divided to 10, because sample size is 10, it will be 0.05, what we have here, right? So now for every sample, I have empirical quantiles. Empirical means based on the values, based on the experiment, right? Now I can compute theoretical quantiles, because now I assume that if my data indeed came from normally distributed population. So what it means? It means that, for example, how to find the theoretical quantile here. I use a quantile function for normally distributed population. I say find a Z-score which corresponds to 5% area on the left. And that Z-score, theoretical quantile will be minus 1.6. So I compute it here, if I round it to 1 decimal, you can see it should be actually 64. I think I made a wrong round, but anyways. So then I compute it for every value that I have. For example, how I got this one. It's Q norm, and then this is the probability, 0.75. If you run it in R, you will get 0.67. So that's a z-score that gives you area on the left equal to 0.75. Now I have x values, I have z-scores computed using this two-steps procedure. Now I just need to make a plot, x versus z, right? So this is just to remind you again why we have quantile in the name. So first we compute sample quantiles based on the ranks, and then we compute theoretical quantiles based, assuming that these values came from normally distributed population, right? So if I make a plot, you can see a kind of a linear trend here. And if I compute, for example, intercept and slope of this line, it will be exactly average and standard deviation of my sample. Okay, so this is exactly quantile plot. And then, so this is the plot that we made manually. And this is how to make it in R. You use the function cuckoo norm. And then for any set of values, you don't need to compute anything yourself. Cuckoo norm will do all the computations for you. But if you compare the plot that I made automatically in R and the plot that we just made together manually, you can see that they are identical, right? So we can clearly see a linear trend here. You can actually add a theoretical line, cuckoo line. You can see that it indeed crosses all the points, and you can see the points kind of line close to this line. So we can indeed see a very clear linear trend here. But sometimes, of course, points can deviate from this line, and we will discuss what to do in this case in a minute. Okay. So quantile plot, it's a plot based on two-steps procedure. First, we compute empirical quantiles based on ranks of your values, and then we compute theoretical quantiles, assuming that these values came from normally distributed population. So we use quantile function, ICDF function for normal distribution, and then we make a plot where we have z-score here and the x values here. You remember that x, we assume that x is mu plus sigma z, right? But it's the same as y is a plus bx, right? So we use z as our values along this axis, right? Sigma, in this case, of course, it's not sigma, it's s. It's the slope of this line, and then mu, it will be intercept. So intercept, you remember, it's where the line crosses 0. It's the value that you have when z-score is equal to 0, so it's the average value here, right? It's the average value here. So that's the overall idea. Now let me show you how cuckoo plot, QQ plot, looks like for different samples and also for when the sample size is really large. So in this case, you can see my sample size is 1000, and this is the QQ plot for 1000 values, and this is indeed sample from normally distributed population. I just use R norm function from R. Then you can see almost perfect linear fit. A couple of values deviate. Usually on the tails, you always have some extreme values that deviate from this linear trend, but in general, you can see most of the values are very well fitted by this theoretical red line. Now let's get back and recall 4 situations that I started this learning sequence with. You remember we have right skewed data, we have left skewed data, we have data with high kurtosis, so it means we have some extreme values on the tails, and then we have bimodality, so we have 2 distributions together. So let's see if a QQ plot can actually detect these deviations from normality, and then you can see indeed it can. For example, for the skewed data, you have a C-shape plot. If you make a cuckoo plot, you will see the points look like letter C. In this case, it looks like letter C shown like this, and in this case, it looks like this, right? So you can see, you can also see a difference between the right skew and the left skew by just looking at the shape of the points. If you have problems on the tails, you can see this clearly here. And you can see much easier to detect these problems on the QQ plot instead of the histogram. And then the bimodality, you can see it's a very clear pattern, like it's like 2 lines, right? You have 2 distributions, 2 normally distributed populations, and that's what also QQ plot shows you. QQ plot is good starting from 4 or 5 points. Even if you have 5 points, you already can use QQ plot to assess if these 5 points came from normally distributed population. But the drawback is that it's a plot. So it means it's subjective. It depends on your imagination. Some people will say, okay, I can clearly see that points follow linear trend. Some people say, no, they deviate from linear trend and so on. So it means that we need another tool which will be a little bit more precise. So it should be numerical tool. So it should give a number, and then we can use this number to assess how extreme our values are in order to be taken from normally distributed population. And that's a normality test. We are going to talk about statistical test in the next block number 2. But let me just give you some very light kind of explanation how to use normality test. The normality test is the following procedure. First of all, we have an assumption, which we call a null hypothesis. And our assumption is that our sample came from normally distributed population. Why is this our default assumption? Because if we indeed have a random sample and all values are independent, and all values are continuous, then by default we know that random values in this world, continuous random values in this world, are likely to be following the normal distribution. So that's why we have this default assumption. And then we have alternative assumption. So if this one, we don't have any evidence to support our default assumption, we can take the alternative assumption, which is our sample didn't came from normally distributed population. And then we make a test. There are many different procedures. There are different methods to make normality test. We will use Shapiro-Wilk test. It's one of the most efficient one. This is how to do it in R. So you just run Shapiro test, and this is your sample. So this is the vector of your values. And then it results with two statistics. First of all, it shows you this one. It's a statistic that tells how big the deviation from normality is. If it's 1, then it's a perfect normal distribution, and then any value that deviates from 1 it means that it's more extreme, so to speak. And then this is the most important. You can skip this one, you can look at this one. This is what is called p-value. P-value, it's a chance to get a sample that looks as bad as you have or even worse, assuming that it came from normally distributed population. So in other words, you can think about the following. If you look at the cuckoo plot, your sample doesn't look like it came from normally distributed population, meaning you have a line and then maybe points kind of deviate from this line like this, right? So it means that your sample doesn't look like it's normally distributed. However, on the other hand, you know that we live in a random world, everything is possible. Maybe this bad sample came from normally distributed population. How likely you can get sample which looks as bad as you have, or even worse, if anyways it came from normally distributed population? That's exactly what p-value is. And in order to reject null hypothesis, in order to reject the normality of your values, you need to have p-value very small. For example, some people use 0.05, which means only 5% chance, if you repeat this, only 5% chance to get a sample as bad as you have, or worse if it came from normally distributed population. Some people use 0.01, which means 1%, and so on. So it depends. The choice of this threshold depends on the situation. So far, we will use this value. So it means that if p-value is below 0.05, we will reject the normality assumption, and we will assume that our sample doesn't follow, or our sample came from population which doesn't follow the normal distribution. So long story short, make a QQ plot, look at the values. If you feel like they deviate from normality, make normality test, and then look at the p-value. If p-value is not below 0.05, then you can continue as indeed sample came from normally distributed population. So you can use normal distribution to describe your sample and to make any additional calculations. Now let me show you several examples. So in all these examples, I have sample sizes 15. And in all these examples, my sample came from normally distributed population because I use this R-norm function to get the samples. But you can see the samples are kind of extreme, right? For example, if you look at any of these 4 plots, you can see that none of the plots shows points following this linear trend nicely. You always have some deviations. For example, here you can see like some non-linear pattern. Here you have outlier. Here you have some outliers. And then this is more or less okay, but still this one, right? So this is more or less okay, but still you have, for example, an outlier here, right? So in all these cases, if you look at the cuckoo plots, you will have doubts if it's indeed came from normally distribution population or not. But if you run the normality test, you can see that in all these cases, the p-value is large enough to accept the normality assumption. So it means we don't see any clear contradiction between the behavior of our sample values and the normality assumption. This is possible. How possible? For example, in 14% of cases, your sample will look like this or even worse. So it means deviation will be even larger, right? In 12% of the cases, it will look like this or even worse. In here, you can see 3% of the cases. So if you have a threshold of 0.05, so probably you will reject the normality assumption here. So it means that this looks pretty extreme. So it's still possible. You still have like 3% of your samples will look like this or even worse. But then if you use threshold of 0.05, in this case, you will reject normality assumption here. Then you can see this is again 24% of your samples, which you take from normally distributed population, will look as bad as this plot, or even worse, but you accept normality assumption in these three cases. Okay. Now, let me show you a couple of extra cases. For example, you can see here, you have very clear outliers, and this is p-value of 0.03. Here you have clear outliers and p-value 0.02. Here you have clear values and 0.01. So in all these cases, the normality assumption will be rejected if you use a threshold of 0.05. And it means that you will be forced kind of to use non-parametric approach, because you cannot use parametric approach, you cannot use normality assumption for these values. But in all these cases, my sample came from normally distributed population because I took it using a special function, R-norm. I know they came from normally distributed population, but they just look extreme, and test rejects the normality assumptions. So my point is that tests also sometimes give you wrong answers. For example, if you use a threshold of 0.05, 5% in 5% answers, your test will be wrong. So you will get a small p-value, although your sample came from normally distributed population. That's something that you need to live with. So this is the summary. If you want to check your values for normality, and you have to do it if you want to use normality assumption for calculations. For example, if you want to represent your data using average and standard deviation, if you want to run different tests that we are going to talk about in the next block, in block number 2, for many different reasons, you need to check the normality assumption, and this is how to do it. First, make a cuckoo plot. It's always a nice idea to start with plots, because cuckoo plot also shows you different possible issues with your data, like outliers, like skewness, like some other patterns. So make a QQ plot first and investigate how nicely your values follow this linear trend. Do you have any outliers and so on? Then make a normality test. And if p-value is not smaller than, for example, 0.05 or 0.01, then you can continue as if this sample came from normally distributed population. You can also compute skewness. It's also nice statistics. It shows you how symmetric your values are. The closer skewness to 0, the more symmetric the values are. And then remember that if you have several populations, for example, if you have samples from different rivers, from different, from different groups, then you need to treat them independently. So if you have samples from different rivers, don't make a QQ plot for all of them. Split them population-wise, river 1, river 2, for example, group 1, group 2, and then treat every sample independently. That's very important. And then let me give you another example. I told you somewhere at the beginning that normality, we expect normality if your values are not bounded strictly, right? But if they are bounded, you will very often see some non-normal distribution. For example, in this case, you can see the quizzes of my students in 2023. I had approximately 155 students. And this is the answers, how well they answered quiz for block number 1. In this case, you can see the percentage of correct answers from 0 to 100. And then you can see that, first of all, I have a very high number of students that have a very low number of answers. So most of them just didn't take any quiz, so it's 0. It means that it's 0, right? If I remove all 0% answers, then this is the new distribution I got. This is also B1, but without 0%. So you can still see the skewness, right? You can see that it's kind of left skew, but you also see that this two bars, they're a little bit higher, right? So if you don't have them, then it will be perfect left skew. So you can see that most of the students actually doing really well. They got percent of correct answers between 80 and 100, but we have a group of students that doesn't follow this trend, right? So in this case, you can't use normality, and for many observations which are bounded, like in this case, you will see these patterns. In this case, you have to use non-parametric description based on ranks, and also if you want to make any tests, you also need to use non-parametric tests. And we will discuss what to do with this kind of data in the very last block, in block number 4, where I have a dedicated learning sequence about non-parametric methods. But in the starting from the next block, we will discuss data which follows different theoretical distributions. So it means that we can use parametric approach to describe this data and also to run different tests. I already showed you this Grasta app where you have different variables. And then you can see the population. So this is a population. And then you can see the sample. And then you can see how this plot, the percentage plot, looks like for your population and for your sample. Also how the box plot looks like for your population, for your sample. I recommend you to try this again, because, for example, IQ in this case will be normally distributed. And then you will see how big the deviation can be, how big the deviation of your sample values from the population values can be for different sample size. So I really recommend you to play a little bit with this app again. It's called Sample and Populations. It's one of the first app in this Grasta, Grasta.com. And then the second app, that's the video that I'm going to show you in a minute. It will be Grasta video, Grasta app video. It tells you how quantile plot works with more examples. So you will see also how this quantile plot can look like for samples of different size and so on. Please watch this video, the next video about this app, and then play with this app. Go to grasta.com, play with this app. It gives you much better understanding how QQplot works. And after that, we will continue with talking a little bit more about how to use normal distribution.